Hello everyone. In the previous lecture, we had set up various definitions in the polar coordinate system uh, that can be utilized for the solution of problems in 2D elasticity. And we had uh, uh, packaged uh, those definitions in a single Python file called polar utilities. Now, our plan for this lecture is to utilize those uh, definitions for the solution of an actual problem, and the route that we will follow is the same as in the classic book Elasticity by Timoshenko and Goodyear. Uh, so first of all, what we'll do is consider a theta independent Airy stress function without referencing to any particular physical situation. And what we'll do is, after discussing the form of the stresses, we will specialize our discussion to a particular axisymmetric problem, which is the problem of the pressure vessel, of the thick-walled pressure vessel. So that's the plan. Let us proceed. So first of all, we have to invoke all the definitions that are present in our polar utilities package. So for that, we use this statement from polar utilities import star, which will import everything that we have there, including the command import SymPy as sim. So you wait a while it loads. All right, it has loaded. So the first order of business is to actually set up an Airy stress function, but unlike our previous class, we will not have a dependence on both r and theta. Rather, we'll have a dependence only on r. Okay, so there will be no theta dependence this time. So phi is equal to there's a function, but the dependence is now only on r. All right, now we would like to have the form of the polar biharmonic displayed to us. So for that, we can just use the command the function definition that we had written down in the polar utilities file. So polar biharmonic is defined there. So if we write this as polar biharmonic of phi, we are getting this form. And please note that this is significantly shorter than the polar biharmonic of phi, when phi was dependent on both r and theta, as was demonstrated in the previous recorded video. All right. Now, as before, we would like to have these things displayed in a nicer fashion, and for that we invoke the displaying capabilities from IPython. And now we can actually display this in a much nicer fashion using the LaTeX rendering capabilities of Jupyter Notebook. So what I want to display here is basically the polar biharmonic itself. So for that, I need to write this as nabla 4 phi So this will be polar biharmonic of phi. Let's see if this thing works. All right, that's what I wanted. So this is now displayed in a very nice explicit fashion. Please note here that this del 4 phi r that is written, it is just the clear-cut typesetting. Okay, so this is the cosmetic part. It is just displayed here, but this is the one that has the actual mathematical life behind it. Anyway, so once we have these things, what we can do is we can go ahead and try to solve this equation directly. Okay, so we understand that the equation that we are trying to solve in 2D elasticity is the polar biharmonic or the biharmonic equation, which is del 4 phi is equal to 0. So if our equation is, so we set up our equation, the biharmonic equation as so everything which is to the left of the comma is the left hand side of the equation, which is the polar biharmonic of phi, and just to the right of this comma is 0. So polar biharmonic of phi is set equal to 0. That is the equation we want to solve. And since this is a differential equation, specifically a fourth order differential equation, what we are going to use is the desolve capability or desolve command within the symbolic Python package. So let's see what this gives us. Sim.desolve eq. Okay. All right. So you see how nicely this solution has been presented to us. Okay, so this is the solution of the polar or the biharmonic equation. Okay, del 4 phi is equal to 0. Now this is a particularly notable solution because although we have found this out in the context of this 2D elasticity, but especially the students, the first year MTech students will study another mandatory course in their second semester, Advanced Mechanics of Solids, and there also in the context of plate theory they will encounter another fourth order equation where the dependent variable will certainly not be the Airy stress function, rather it will be the displacement in the z direction, but the equation is exactly the same. Okay, so it is the fourth order derivative of w that they have to solve there, but the solution form turns out to be exactly the same. So this is a rather important equation, this fourth order involving the fourth order derivative. Now because we are following the route of or the presentation given in Timoshenko and Goodyear, we would like to have these this solution form exactly as it is presented in that book. So there, instead of the C1, C2, C3, C4 constants, the constants A, B, C, D are used. Okay, and in a slightly different order. So we'll follow that book exactly. So we set up the symbols, or define the symbols first of all. That's done. And what we'll do is we'll set up our phi as, so this C4 log R term, that is the one involving the A. So sim dot log R plus B. So this C3 R square log R term, that is the one involving B. We just manually type it in, not that long. The C2 R square is C, and finally the constant term C1 is D. Okay, so let's display this once more in a nice fashion. So display math. All right, so that's exactly what we wanted. Now, now that we have in our hand the form of this Airy stress function, we can immediately find out the forms for the various stress components in this polar coordinate system. Meaning to say that we can immediately find out sigma RR, sigma theta theta, and sigma R theta. Now, please note that because we have already imported all the things defined in the polar utilities file, and if you refer to the previous video, you will see that even the definitions of the stress components sigma RR, sigma theta theta, and sigma R theta are already defined there. All that I have to do is just invoke them with their proper names. So the definition, the function definition for that was sigma underscore RR for sigma RR phi. And what I will do is I will assign the result of that in this sigma RR variable, okay, without the underscore. So with the underscore, it is the function call, and without the underscore, it is just the variable name, okay, that I'll use to as a variable name for this expression of sigma RR. In a similar fashion, for sigma theta theta, I'll use this, and for sigma RT, of course, I'll use this. And now I want to display this in a nice fashion. So again, as usual, I use my IPython display capabilities. I can copy this thing because it is quite repetitive in nature, and for this display I actually use the theta theta. Alright, let's try this. Okay, so this has been displayed very nicely here, and you please note that the sigma r theta is indeed coming out to be 0. Now now this is the part where we slowly proceed to referencing actual physical situations, because the discussion till now has been only about utilizing all the function definitions which are there in the polar utilities file, with the only special thing that we have done here really is that instead of an area stress function that was generally dependent on r and theta, the one that we have taken today is just the one that is dependent on r. That's the only special thing that we have done, and of course we have done this solving of this equation also. Other than that, we have not done anything special with regards to any particular problem. Now you see, because we are considering an area stress function which is not dependent on theta, it gives us an indication that this is perhaps suitable for axisymmetric kind of problems. Okay, this is a natural choice. This would be a natural choice for an axisymmetric kind of problem. Now, axisymmetric problems can be of various different types, but one important thing which we have to remember about these axisymmetric problems is the geometry that we are considering, the domain, the physical domain that we are considering. Okay, does that geometry or physical domain, does it contain the r equal to 0 point? That is a very, very important consideration to think about. So all of you have been through your undergraduate classes, and these are the kinds of considerations which you had to keep in mind, even though probably you did not realize it explicitly, but you had to take care of these things back when you studied fluid mechanics, or for example flow through a pipe. Okay, so flow through a pipe and flow through an annular pipe had different considerations. Similarly, when you talked about heat transfer, okay, so for example heat transfer in a circular rod or in an annular section, so things were different, because in the circular rod the r equal to 0 was very much part of the domain. Now, why is it such an important thing to be concerned about? You note, to answer that, you note this sigma rr and sigma theta theta terms. Okay, so back to 2D elasticity from fluid mechanics and heat transfer, you note this sigma rr and sigma theta theta. Both these terms, they have this 1 by r square and log r term, 1 by r square and log r term. Now, at r equal to 0, these two terms are problematic. Okay, they tend to minus infinity. Okay, so this log r, it tends to minus infinity. This r 1 by r square tends to infinity. Now, because we are dealing with real situations and we do not expect our stress values to spike like that to infinite values, what we'll say is that if we consider a circular domain which does not have any hole in it, okay, I repeat, if we consider a circular domain which does not have any hole in it, where of course that hole would be encompassing that r equal to 0 point, then we have to drop these terms involving the 1 by r square and the log r term. Okay, so that's what we write. So let me convert this current cell to a markdown cell so I can put in this comment. So escape, and then I press M to convert this to a markdown cell, press enter to edit it. Okay, so for a domain with no hole, including or with no hole containing r equal to 0, the terms involving a and b must be dropped. Okay, so that sigma rr and sigma theta theta do not give infinite values. So what we'll have is for sigma rr no hole case. Okay, so let's set up a new variable called sigma rr no hole. All that you have to do is we call the sigma rr, but then we substitute a is 0 and b is 0. Okay, so let me write that down. We substitute a as 0 and b as 0. Similarly, for sigma theta theta no hole case, a is 0, b is 0. And now if we try to display this thing in a nice fashion, to type out all that, but the end result is quite visually pleasing, so I'll go through the effort a little bit. I don't have to worry about the sigma r theta because that is identically 0. Okay, there are no a b c terms there, so nothing to worry about for sigma r theta. So let's display this. Now we know for sure that of course when a is 0 and b is 0, we will have only the twice c terms left. I did not have to do all this symbolic Python business for that, but I just wanted to demonstrate once again for the purpose of your practice that how do we go about substituting the values like this. Okay, maybe in a different situation you need to substitute different things, so how do we go about doing that? All right, now that we have this, we can also next consider so important thing is that when we do have a no hole situation and we are proceeding from an axisymmetric consideration where the area stress function is theta independent, then we end up with this kind of constant stress values. Okay, but the situation is going to be different when we do have holes present. Okay, so holes including the r equal to 0. Okay, so what we do is we again use this markdown cell. Okay, next, if we do have a hole including r equal to 0, then what is going to happen is that we can have various different kinds of solutions. Okay, then and various different solutions are possible. As a special choice, let us consider the situation where a is not equal to 0 and b is equal to 0. Let us consider this special situation and you will see the motivation behind this in a moment. Okay, we are considering this special situation. So now our focus is on considering a domain, a circular domain which does have a hole inside it, and that hole includes this r equal to 0, so it is concentric about that. uh, uh, so concentric with the outer periphery or the radius of the entire domain, this hole, uh, and as a special choice we are considering this a not equal to 0, b equal to 0. So what happens now? Well, we can go back to this kind of is of a can go back to these expressions with slight modifications. I won't type them again in order to save some time. So now we are considering the whole case, and now I don't have to set my a comma 0. I only need my b comma 0. So b will be substituted as 0, a will not be substituted as 0, and I will also display this in a proper fashion, taking care to change the variable names, of course. All right, let's display this. Now, these particular forms for sigma RR and sigma theta theta, you probably recognize this from your undergraduate studies. Okay, so I think in most of the mechanics of solids or mechanics of materials classes in undergraduate in our undergraduate studies, this particular chapter is very much covered, axisymmetric. Of course, the route that is followed there is quite different. You probably followed the route that you solved the displacement field, the second order differential equation involving the displacement field in the radial direction, and you probably ended up with a displacement field solution which was like some constant times r plus another constant divided by r. So if you proceed from there and try to find out the expressions of the stresses, you will end up with this kind of a form where there is a 1 by r square dependence along with a constant term. Okay, now this entire discussion till now, at least in this file, it has been devoid of any reference to any particular problem. Now let us see if we can actually refer to a particular problem which is exactly like this kind of a domain. For that, I will go to my writing app and show you this picture. Okay, so we have these two concentric circles, and please note that this is like the end-on view of a pressure vessel. This is the kind of pressure vessel where the pressure from the outside is denoted by this P out, and the pressure from the inside, that is this P in. I have also denoted the inner radius as A and the outer radius as B. So you understand that the material from which this pressure vessel is made is present within these two circles. Okay, this inner circle is probably filled with some kind of pressurized liquid. Okay, so that's the geometry we are considering. Okay, so this is an axisymmetric situation. It is axisymmetric because of the geometry as well as because of the axisymmetric nature of the loading. So these 2 points are extremely important. You cannot have an axisymmetric problem if only your geometry is axisymmetric whereas your loading is non-axisymmetric. So both the loading as well as the geometry must be axisymmetric for it to be referred to as an axisymmetric problem. So that those two conditions are very much satisfied here because the P out and P in are very much uniform all along the peripheries, the inner and the outer peripheries. So we are good. Okay, so this is the kind of problem we are trying to solve here. So the sigma RR hole and the sigma theta theta hole, those will be the stresses, the radial and the hoop stresses in this particular area. Okay, and you take any point within this zone, at that point you will have a particular value of sigma RR and but some value of sigma theta theta. Let's find out what those will be in response to these boundary conditions of P out and P in. And speaking about boundary conditions, we must be very careful in setting it up properly. So that's what we'll do. So let me go back to the Jupyter notebook file. I'll state the boundary conditions So you all understand that we are now focusing on this pressure vessel problem. Okay. So for the boundary conditions, we have, let me write this down quickly here. So sigma RR will be equal to minus P in at R equal to A. That's what we want. At R equal to A. And the same thing at the outer boundary, sigma RR is equal to this time minus P out at R equal to B. So these are the boundary conditions we are looking for. Okay, so where P in and P out are the pressures on the inner and the outer periphery respectively. Okay, so with that stated, let us actually define these symbols P in and P out. Let's also display this so we know that we have typed everything properly. All right, so that's done. Let us also remember that we need to set up our A and B variables. Okay, the inner and the outer radii. So let us adhere to the Python community encouraged best practices of specifying a certain variable to be positive when we know for sure that they are indeed positive. So A and B are both radii, they are positive quantities. So we state that. Okay, it won't make any difference, but it's good practice. All right. So with these out of the way, we need to specify our boundary conditions now. Okay, so for that, what we'll do is we have to substitute in this sigma rr whole variables. You please note, okay, I'm going back a little bit. So in this sigma rr whole expression that we have, okay, here what we'll have to do is we have to substitute r equal to for this sigma rr whole, r equal to a, and then I have to set that to minus p in, and when I set r equal to b, I have to set this equal to minus p out. So that's what I'll do. So I'll explicitly set it up like the LHS and the RHS. So I'm first considering this boundary condition sigma rr equal to minus Pn at r equal to a. So for that sigma rr whole subs, I need to set r equal to a. And the right hand side of this equation will be minus Pn. So that my boundary condition number 1 will be LHS1 comma RHS1. Let me also display that. Next, in the same cell, I will set up my second boundary condition, which is sigma rr equal to minus p out at r equal to b. So again, sigma rr whole subs r as b, substitute r as b, and RHS2 is minus p out so that the actual statement of the boundary condition is in this form: LHS2 RHS2, and I'll display this equation also. Alright, so these are my two equations, and these are two linear simultaneous equations involving the unknowns A and C. All that I have to do is use the symbolic Python linsolve command to solve for this. This we have already done earlier, this kind of a solution previously for that simply supported beam problem. And I also need to specify what are the things I'm solving for here. And please note that I'll assign the solution to this variable. Now I can display the solution like this. Let's see what it gives us. Okay, so it gives us the values of A and C in this packaged within this solution variable. Now I would like to have these things explicitly in my hand. Okay, so instead of displaying it like this, what I'll do is I'll assign this to the variable called A solution and C solution like this. Okay, it is extremely important that we maintain the same order of the variables here. Okay, so the solution, the first element in this solution, which is indexed by the solution by the 0, that has to be assigned to the first thing which is present here. Okay, so had we placed it like C comma A, there is no restriction which is telling us that it should be like A comma C. We could very well have written this as C comma A, but if we had done that, then the solution 0 must be assigned to C solution. Okay, similarly for the other case. Okay, so now everything is fine. And what we can do is we can also display this thing so that everything is nice, clear and explicit. I'll just copy this and paste this and just make the appropriate modifications. Okay, all right, this is the form that I wanted. So all that I have to do now is substitute these solutions for A and C back in my expressions of sigma RR and sigma theta theta, and I'll be able to write them down. Okay, so sigma RR whole, but this time with the solution term added here. So this will be just sigma RR whole, but where I'm going to substitute in A the A solution and in C the C solution. So please note this carefully. What I'm doing is I'm taking the variable sigma RR whole, and what I'm doing is I'm substituting A solution in A and C solution in C, because in a piece of paper that's exactly what you would do. Similarly for sigma theta theta, I don't have to change anything on the right hand side. All that I have to change here is this sigma tt. Okay, and finally I can just display this nicely. Sorry about that. And next for the sigma theta theta. And that's it. Okay, so I can do a little bit of a beautification here by writing this as Roman. Doesn't make any difference, of course. All right, so this is the solution of the pressure vessel problem. Okay, now with these things set up, okay, you can play around with uh, uh, with this P in and P out. Maybe you need a solution for which P in is perhaps some finite value, but the P out is 0, or maybe P in is 0, P out is some value, or any other combination that you can think of or face in an actual problem situation. Okay, so this kind of a general framework is very much amenable to uh, to modify and to easily test out the solutions. You can also take these things, uh, uh, make them amenable for numerical calculations, uh, and very conveniently for plotting purposes also. Okay, so with this, I have come to an end of this particular demonstration. Uh, so please note what we have done here. We have started out with the theta independent phi eddy stress function, and ultimately we had ended up with a solution for the pressure vessel problem, the familiar pressure vessel problem, which you had solved by a different route in your undergraduate days. Okay, so uh, uh, I hope this will be a good first introduction to the way that problems can be solved, and in the next lectures we'll address more involved problems and more interesting problems. Thank you very much.